The question says that a complete binary min heap is made by including each integer in the interval 1, 1023 exactly once. The depth of a node in the heap is the length of the path from root of the heap to that node. Therefore, the root is at depth 0. The maximum depth at which integer 9 can appear is. Okay, so this is a numerical question and you have to calculate the answer. What would be the depth, the maximum depth at which integer 9 can be present, and then fill in the blank. So if we have to find out the maximum place or the position, the farthest position from the root, what we can do is, instead of filling the min heap or the binary min heap completely at each of the levels, we make it a skewed binary heap, or we make it a skewed tree, so that each node or each number is farthest as possible, and we continue this till we reach the number 9. Okay, so what I'm exactly saying is that we have to start, since it's a binary min heap, therefore we'll be starting with a minimum value which is 1. Then if we have to place 2, there are two options, right child of 1 or left child of 1. Okay, then to place 3, I can place it as the next child of 1, but since I have to assure that 9 is at the maximum depth, and by depth I means it is at the farthest distance from the root node, therefore I'll ensure, or I'll make this prominent here, that every number that is less than 9 and it is appearing in this heap should be at the farthest position, so that eventually 9 also falls at the maximum depth possible. So if I make a left skewed tree like this, filling in all the numbers till the value 9, then what do I observe is that though 9 appears at the farthest end, this is the farthest depth that can be achieved for placing the value 9, but this is not a complete binary min heap. Firstly, it is not a complete tree, it is not a binary tree, and it is, though it's a min heap, but it should follow the first two properties. So what we have to do, to make it as a complete binary min heap, we need to fill all these levels completely. So all the levels that are present at any particular depth, all the previous levels must be completely filled, then only we can place a node in the next level. Okay, so to place 9 at this farthest point, I have to fill all these levels first, and to completely fill them. So what do I mean by completely filling them? That at every level I have to place all the nodes, the maximum number of nodes that can be possible. So if this is level 0, it is root node, so number of nodes that can appear, maximum number of nodes that can appear are 2 raised to power 0, which is 1. I have placed one node here. This is level 1. Maximum nodes that I can place here are 2 raised to power 1, which is 2. This is level 3, level 2, level 3, level 4, then level 6, level 7, and level 8. Alright, so this comes out to be 256. Now these are the number of nodes that are possible for each level. That means at level, this is level 2, 3, 4, 5, 6, 7 and 8. If we have to place 9 at the farthest level, which is depth 8, Okay, then I have to completely fill all the above nodes, and then only this complete binary tree would be possible. And why are we checking that we are able to fill this or not? Because we have to place 9 at the farthest end. We can place 9 at the maximum depth by placing it in a skewed manner, and if I am placing it in a skewed manner, I have to check whether I can fill the above levels completely or not by the given range. So if I sum up all these values, that means the total number of nodes that I would get would be 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 plus 256. If you sum this up, you will get a total of 511. Okay, or 511. Okay, so 511 or 512 nodes that you will get as here is a subset of the numbers that you are provided. So you have to make a complete binary min heap using this range only. You cannot go beyond this range, and using the numbers within this range, using around 511 or 512 numbers, we can make this complete binary min heap and place 9 at the maximum depth of 8. So this is possible, and the answer would be 8. Please ensure that if you are placing a particular value at the largest depth by doing such a arrangement, left skewed or right skewed, then you have to make sure that the number of nodes appearing in the previous levels are equal to the maximum, equal to or less than the maximum number of allowed nodes that you can place there. Okay, so coming to the next question, the question states that the B plus trees are considered balanced because the options, 4 options that are given to you are: the lengths of paths from the root to all the leaf nodes are all equal. The second part is: the lengths of paths from root to all leaf nodes differ from each other by at most 1. The number of children of any two non-leaf nodes, that is siblings, differ by at most 1. And D, the number of records in any two leaf nodes differ by at most 1. So in B trees or in B plus trees, you have to remember that the main concept or the way by which that these trees remain balanced, or they maintain their property of being balanced at all the levels, is that during insertion and deletion, they ensure that the length of the path of all the leaves from the root is equal. That means all the leaves are at equal lengths from the root. Okay, so by reading all these options, we clearly know that the length of paths from the root to all the leaf nodes are all equal is the correct reason for B plus trees being balanced. Now you must also remember, I always tell you to remember the concept behind various properties that actually occur in various data structures and other computer subjects as well. So what is the concept and how this balance property is maintained? While insertion or while deletion, B plus trees as well as B trees make the root to move at a new level instead of making any changes in the intermediate node. So what I actually mean is that at the time of insertion, if we have to increase the height of the tree, so we increase the height from the root. Okay, and similarly we move the root to a lower level, or we move the root one level down in case of deletion. So insertion and deletion in B plus tree ensure that the trees remain balanced. Okay, and how do they ensure? Just now as I explained, we In case of insertion, we increase the height of the tree if required by increasing or moving the root, the level of the root up. Actually, the level of the root would still remain 0, but we move the root further up. And in case of deletion, what do? We bring the root at a lower height if required, rather than bringing a node or changing the position of different nodes. Okay, with internally we change the position of the root in both these cases, so that the length of the path from the root to all the leaves remains the same in all the cases. Because if root is increased by 1, then the path length will increase by 1 for all the leaves. If the root is decreased to a lower level or a lower height, then the path length will decrease for all the leaves. The path from the root to the leaf would always be affected equally. Okay. So that's all for today's lecture. In today's lecture, we saw two slightly twisted questions on data structures topic. If you have a clear understanding of the concepts, these such kind of questions won't be very difficult for you. So thank question. The question says, in a connected graph, a bridge is an edge whose removal disconnects a graph. Which one of the following statements is true? So the first option is, a tree has no bridges. Okay, so a tree has no bridges. This statement is not correct. See, if I say that I have a simple tree with 3 vertices or 3 nodes, then this is a tree. And if I remove any of the 2 edges that are present, then I would get something like this. So basically, I remove an edge and the graph becomes disconnected. So basically this edge that I removed was a bridge, or it was a bridge edge. That is why this statement is false, and we cannot say that a tree has no bridges. A tree has bridges because the node that is connected to its parent is always connected by a single unique edge. Alright, so this statement is false. Now coming to the second statement. The statement says a bridge cannot be part of a simple cycle. Yes, this is perfectly true. And why is it true? Because in a cycle, let's again take an example. See, this is a simple cycle again with 3 vertices. And in a cycle, every vertex will be connected with other vertices in more than one ways, or using 2 ways or more, because in cycle there are redundant edges. The removal of such redundant edges will not disconnect the graph. They will make the graph connected even when these edges or these redundant edges are removed. Okay, so let's say I remove this edge from this graph or from this cycle, and I'll be left with this remaining tree or this particular graph without this edge. This resultant graph is still connected and it did not disconnect the graph. Therefore, a bridge cannot be part of a simple cycle, because a bridge disconnects a graph when it is removed, but in a cycle every vertex is connected to other vertices using more than one ways. All right, so there is no option of being disconnected. Now since you are given that only one of the statements will be true, you can stop at option B, but for confirmation purposes you can proceed with reading option C and D. I always suggest you to go through the entire question so that you do not make any silly mistake. So we'll consider the next options as well and see what do they actually say. The C option says every edge of a clique with size greater than or equal to 3 is a bridge. Now this statement is false because what is actually a clique? A clique is any complete subgraph of a graph. Now any complete subgraph, to disconnect such a graph we always require n minus 1 edges provided there are n vertices. So for a clique with n vertices, since it is a complete subgraph of a particular graph, you will require n minus 1 edges to disconnect this graph. Alright, therefore every edge of a clique is a bridge is not correct, because similarly, just as we said in the previous part, that removal of any particular edge would not disconnect a graph. Therefore we can't say that every edge is a bridge edge. Alright, now coming to the D option, a graph with bridges cannot have a cycle. No, this is also false. The C statement was false and D statement is also false. Let's make a graph which has a cycle, say this graph only, and let's make a bridge edge. Now if I remove this edge, the graph, these three vertices would become disconnected from this fourth vertex. Alright, therefore this edge is a bridge edge and this is a cycle. Therefore this statement is not correct, that a graph with bridge edges cannot have a cycle. Therefore the correct answer is option B, or part B. Alright, now coming to the second question of this lecture, the question says, consider the following array of elements, and you are given an array 89, 19, 50, 17, 12, 15, 2, 5, 7, 11, 6, 9 and 100. The minimum number of interchanges needed to convert it into max heap is, okay, so a max heap is a binary tree in which a certain property is satisfied, that at every node, the, or you can say the parent node is always has it always has a value that is greater than the value present at the child nodes. Okay, so let's start the construction of this tree according to the array that is initially given, and then we'll see how many interchanges would be required. So if you are given such an array, you must know that you have to construct the array in the given order only. So this, the first edge becomes 89, then you go to the next edge, the second element would become the left child and the next element would become the right child of the initial edge. So 89, left edge is 19, then right edge is 50, then 17 would again come, or it will occupy the place that is to the leftmost of the current constructed heap. Okay, so this would occupy the place of the left child of 19, then 12, the next empty place, then 15 would come here, then 2, then 5, then 7, 11, 6, then 15 would have a child of 9, and the last element is 100. So 2 does not have any children. Now let's see at what positions the max heap property is not satisfied, alright, or it is disregarded. So we have the root as 89, both the nodes or both the children of the root should have a value lower than the value present at the root. So 19 and 50 both are less than 89, alright. So now let's check for 19 as a parent. 17 and 12 both less than 19. Now for 50, 15 and 2 are both less than 50. 5 and 7 less than 17, 11 and 6 less than 12, 9 and 100 are not less than 15. So how many interchanges would we need? See, this is the node which does not have the correct value. Obviously, its parent should have a higher value. So whenever we max heapify a particular array or particular heap that is given to us, we exchange the value at the child with the value at the parent. So if we bring this value upward and exchange it with its parent, what would this tree become like? This would become something like 89, 19, 50. I'm not drawing the children or the child tree of 19 because that would just remain the same. I'm just expanding the right child of 89, which is 50. So if I exchange 100 and 15, what would come? Here 2 would be present as it is. This would become 100, this would be 9, and this would become 15. Now let's see if any other property is violated. 100 has its two children which are lower in value. Now 50 has one of the child which is greater in value. So the nodes that are in error are 50 and 100. In the next step, we would again exchange the values of these nodes. The tree at 19 would remain the same. Here 100 would come, the left child of 100 would become 50, the right child would remain 2, and the two children of this node would be 9 and 15. Now let's see. 50 has two children lower than the 50 value, 100 has two children less than its value, but 89 has a child which has a higher value than itself. So again we need to make another exchange. So 100 would be at the top. The final tree would look like this: 52 and 9 and 15, and this would have the same tree. Sorry, this was 19. All right. 17 and 12 and the two children. All right, so how many exchanges have we made? We have exchanged 15 and 100, which is first swap, then 50 and 100, which is the second swap, and 89 and 100, which is the third swap. So we have made 3 exchanges to form it the max heap. Why max heap? Because if you check in this tree, every parent would have a value that would be greater than the value of both its children. All right, so the correct answer is option D, which is 3 exchanges. So that's all for today's lecture. If you understood these questions, please like our video, share it with your friends, and let us know your feedback. Subscribe to the channel of Easy Engineering Classes for more such tutorials in our preparation series. Press the bell icon to get the notifications of our upcoming videos that we upload in future, so that you do not miss any video. Thank you for watching. Good luck for your exam.